This is a review of what we talked about the other day. This is the concept slide for preloading fasteners. The concept is that we are going to wind up the material by putting a lot of load into the fastener, so the fastener ends up with a high tensile stress, sometimes pretty close to yield. And we also wind up the material in the compressive direction. So we're building in what amounts to compressive residual stress in the material so that it will be able to protect us from fatigue loads that appear on the system. Now, the system is the combination of the materials and the two materials clamped and the fastener. And the load is actually going to be attached not to the fastener, as I show here, but to the materials in the real sense. But this schematic example is trying to show that if I wind the material spring up and I lock it in place with, let's say, a 100-pound load, I can then hang up to 100 pounds on it, and the fastener, the bolt, does not know that I've done it because there's still only 100 pounds in the bolt, and the material is actually taking care of that load. Until I increase above the preload, then my little stop falls out and they separate. That's the concept. Now, in a simplistic application, I might have a pair of cylinders clamped together with a single bolt. This isn't very useful, but it serves as a starting point to point out that I need to find the stiffnesses of the material that is in the clamped zone. We'll talk more about how to do that today. And I have to find the stiffness of the bolt. Now, the stiffness of the bolt is pretty straightforward because we know that it's a round thing in tension, so the stiffness K of the bolt is simply AE over L, where A is the cross-sectional area, E is Young's modulus, L is the length of the part of the bolt being stretched. But because I typically have some threads in the clamp zone as well as the shank, and they're different diameter, then I have to do a two-part calculation, typically for this K sub B, which is the K of the bolt, using the A sub T, which is the tensile stress area of the bolt in the threads, and the A of the bolt, which would be the shank itself. The E of the bolt is going to be the same in both cases. So LT is the length of the threads, and L minus LT is the shank. The material constant in this simple example, where I have defined geometry for the material and it's small, it's just surrounding the bolt, I can make the assumption that the entire barrel of that cylinder is under uniform load because it's small in diameter, only a little bit bigger than the bolt. And so I can apply the same kind of formula to it using the area of the materials, which presumably are the same, but they could be different, so I have two different terms. If they are different materials, then I can simplify the equation. This accounts for the two different Young's moduli. So I might have a piece of aluminum clamped to a piece of steel, for example. This leads to this diagram, which I've found is a little hard to understand when you first see it. So it's worth going through it again, because I'm going to move from this to the more complicated diagram where we have time-varying loads. This is for the static case. So I'm just going to put some preload in the bolt and then apply a static load to it. And the static load is going to be called P. And the loads in the bolt are going to be called F. That is the initial loads in the bolt, at least. Well, actually, the final load as well. So the resulting loads in the bolt and the material I'm calling F. The external load I'm applying to the system, which in the previous drawing would be P over 2 times 2, is this thing called P. Now, looking at the top panel, when I first wind up the bolt with my preload, which I do with a wrench. So I take a wrench on the nut, typically a torque wrench, so I can measure the torque, and I take it up to some value, which we'll talk about in a minute as to how to determine what that torque value should be for a given preload. And as I said, we're going to take it up typically fairly high, so I have a lot of stress in the bolt, which is counterintuitive, because usually you're trying to get the stress down. So here we're deliberately jacking in a whole bunch of stress into the bolt. And what the result of that is that since I have stiffnesses for both the bolt and the material, and typically the bolt stiffness is less than the material stiffness. Why? Because there's less of the bolt than there is material, right? So the slope of the KB line is less than the slope of the KM line, and they go in different directions because KM is going into the compression zone and KB is going into the tensile zone, which is positive. Compression is negative. So when I crank the force in the bolt up to F sub I, which is the initial force, or initial tension, I will have deflected the material delta M and deflected the bolt delta B, right? And they are clearly different. Even though the forces are the same in both, it's the same force, the deflections are different because the stiffnesses are different, right? So the material moves a little bit, but the bolt stretches more and goes to a new length. Now I come along with my load P, and I apply the load. And that load turns out to be shared partially by the bolt and partially by the material, and the material gets the lion's share of it, which is what we want. In essence, what I'm doing is unloading the compression of the material that I built in with my external load. So I'm trying to stretch the spring, in essence, okay? I'm undoing some of the clamp that I built into it in the first instance. And the net result of that is that I have only a small additional amount of load shows up in the bolt, and most of it goes into unloading the material. That makes sense? So with these simple equations, which are just additions and subtractions, I can now develop relationships for the piece of the load, P, that goes into the bolt versus the material. And you see that here, and it's simply the ratio of their two stiffnesses, right? So PB is the bolt force that's added to the initial force, Fi, of course, and it's KB over KM times PM. So that relates the two pieces of it, and I can rewrite that equation, as you see in the next bar, and get an expression for PB in terms of the original load P, which is the only number I know at the outset. And by combining the two, as you see, I get KB over KM plus KB. A familiar looking expression, by the way, for things in series. And we call this expression, this fraction, K of bolt over the sum of the two K's, big C. And it's called the joint constant. And it's constant because once I have a bolt of a certain K and a material of a certain K, I got a certain value of C, right? So using that value of C, which comes about from this simple calculation, I can determine what fraction of my load is going into the bolt and what fraction is going into my material. So C times P is PB, and 1 minus C times P is PM. Okay? So now I have those two numbers. And from this I can determine what the preload should be, the bolt load rather. I can get a safety factor against separation, because if I keep putting in more load P, eventually I'm going to unload that material completely, right? And lose all of my preload. And then I start to put all the load into the bolt directly, as if there were no material there, which we don't want. So we can create a safety factor against what's called joint separation. In these instances, if the joint separates, it's going to be dead very shortly. So you don't want that to happen. So now I'm going to change the problem to a more realistic one, and really the one in which this has the greatest advantage. And that is, I'm now going to have a time-varying load P. And it could be either fully reversed or not. That's a detail that we don't need to go into at this point. But it's varying from plus or minus something. Actually, I don't want it to go negative. I'll retract that. I want it to always be positive, the same direction. So P is, as you see here, oscillating over this P max that you see in the right-hand frame. This is the same picture we saw before. This is after I've preloaded the bolt. So I've wound up the material, I've wound up the bolt. Now I come along with this P, which is a sine wave type of oscillation of force. And just as before, I can divide that into two pieces. And I can find the alternating piece, which is this chunk, which is the FB. And also it's half of FB, actually. It's FB minus FI over 2, as you see here. That's this distance right here divided by 2, right? Because that's a sine wave that has a plus or minus half of that height. And the FM, the mean force that I'm seeing in this joint system now, is half of this distance. FB plus FI over 2. So we now have an alternating force and a mean force, and we're going toward a Goodman line problem here. And from these values of force, I can calculate the alternating stress component, sigma sub A. And I'm probably going to bring in some stress concentration factor at this point, which is going to be appropriate to the threads in the bolt or the radius under the head and things of that nature. So this is now becoming a standard fatigue failure analysis problem once I've identified the forces. And I will have a corresponding KF mean, which may or may not be equal to KF depending on the circumstances. We took that up in Chapter 6, so all that stuff from Chapter 6 still applies in terms of creating these values. And I have a mean component of stress. So I have a classical Goodman line problem, right? I've got a mean and an alternating component. I've got to find the safety factor that is resulting from both of those. But one major difference between what we did with the Goodman line before and this case is we have this initial force and thus an initial stress cranked into this thing that shifts everything up. So I'm not starting at 0. I'm starting at Fi for force. So I need to calculate the stress due to the initial force, Fi over A, times some mean fatigue concentration factor. So here's my Goodman line picture. It looks quite a bit different than the ones we've seen before. We create the Goodman line in the same way. We have to find an S sub E with the appropriate zoo full of factors for, load and surface and size and reliability and all that stuff. So we get our strength parameter for the material in endurance. I'm assuming it's steel, so I've got an endurance limit. You very rarely meet bolts that aren't steel. And SUT for the material over here, and the line between those 2 points is my so-called Goodman line. And inside that line is considered to be safe against fatigue failure. Outside that line is failed. The line is the demarcation, the failure point. So on that plot, I'm going to plot first sigma I, because remember, I cranked the stress way the hell up with my torque wrench before I ever put the outside load on it. And then I'm going to have a very small, relatively small sigma A sitting on top of that, right? And notice how close sigma M is here to sigma I. So this is sigma A, comma, sigma M right here. And my line of potential failure is from sigma I, this dotted line. It's almost vertical, going from sigma I on the axis up through this pair sigma A, comma, sigma M, just as we did before, but before we were doing it from 0. And we went over up sigma A and over sigma M and drew a line to find out where it crossed the Goodman line. And we're doing exactly the same thing here, except that we've shifted everything over to sigma I. And at some point, that pops out of my Goodman envelope, and the safety factor is this length from the breakout point back to sigma I divided by this point, this distance here. And you can see I have a fairly small safety factor there, probably 1.2 or something like that. But notice I've got a 90% preload or something like that in here. So it's quite possible that I might break through the SY line here before I break through the Goodman line, and that looks like it's the case here. I'm going to fail in yielding because I'm going to actually go out through the yield line before I get to the Goodman line with this particular example that I show. So we have to do two checks. We check against whether we're breaking through the Goodman line and separately whether we're breaking through the yield line. That will depend upon the particular data in the problem. So if I take those equations for a given situation, and these plots will be data dependent because it depends on how big your bolt is, what your load is, and so on and so forth. So you have to generate this kind of a plot for every case. So I'm plotting against the preload as a percent of proof strength. Remember, proof strength is approximately yield strength, but it's a published strength for the bolts that they guarantee they will take. And the hash marks on the head tell you what class bolt it is, and thus you can look up the proof strength. So here's the plot of the safety factor against yielding, which, as you might expect, is coming down quite rapidly as I crank in more preload. And of course, when I get to 100% of proof strength, it's going to yield, right? So I don't want to go that far. This is the safety factor against separation, which I showed the equation for a few minutes ago. And this is the safety factor against fatigue. And notice that it's in the less than 1 regime. All the time it's separated. If the safety factor against separation is less than 1, then it has separated, right? This is the point at which it comes apart or not, depending on whether you're left or right at that point. So the fatigue safety factor has a discontinuity. It suddenly jumps up to something larger than 1. And notice how it changes hardly at all as I crank in the proof strength. So you can think of this amount of preload as a minimum threshold over which I have to step before I have any protection at all, right? So it's up to your engineering judgment as to how much above that you go, and that will take into account such issues as the safety factor against separation. I might want to have a good hefty one of those, like maybe a 3. That would get me up to 50% of proof, at which point I would have a pretty good yield number. And notice where these two guys cross might be a good optimum design, right? Because I've got the best combination of yield safety and also separation safety where those 2 points cross. And my fatigue safety isn't making much of a difference. This line I don't think is actually exactly horizontal, but its slope is so low as to be almost inconsequential. Now, all of the books I've read on this subject, and there are hundreds of them, they all make the same statement. They'll say, you should always take it up to 90% of proof. And I said, okay, that sounds interesting. And then I started to do this study when I was writing the book. And I did a whole bunch of different examples, and I'm not sure I agree with that flat statement. Because it looks to me like on this problem, I'd be better off to have less. Because if I crank up to 90%, what's my yield safety factor? It's like 1.1, right? It's less than my fatigue safety factor. So if I back up to where they cross, that's 80%. So I could get a commonality between NY and NF right here, but I don't have much for separation either. I've only got like a 1.4 against separation? That seems to me a little thin. So when I do these problems, which I don't do that many of them professionally, but when I do run into one of these, I do a plot like this, and then I make my own judgment. You know, where do I want to be in that picture? And remember, these curves will all look different depending on your data. This is just a generic example. So if you have more load, less load, more K, less K, or whatever, you could get a different set of numbers coming out of this thing, and the crossovers will come in different places. But this kind of a plot, this is sort of as an aside, in design engineering, this sort of an approach is, in my view, the best way to go at any problem. I want to see how these variables of interest, safety factors in particular, change with parameters when I introduce different factors. And visualizing it on a set of plots like this is really helpful. It takes me right to a good solution. And with the computers we have available, that's a piece of cake to do. Okay? Any questions at this point? I'm going to change the subject slightly on this business of preloading to protect against fatigue failure. Okay. The biggest Achilles heel of this whole computational process that we're talking about is getting a value for K sub m, the stiffness of the material, which, as you can tell, makes a big difference because that's going to determine C, the joint factor, and everything else depends on C. So if I don't get a good estimate of K sub m, then this stuff isn't worth very much. And until very recently, like 3 or 4 years ago, there was no good method to solve for K sub m. And therefore, there were all sorts of estimate methods that were proposed. And I used to have them in this textbook until I discovered this paper. I was actually asked to review this paper, and when I read it, I said, holy smoke, this is like the holy grail for preloaded bolts. And so I incorporated his paper with his permission into the latest edition, which you have, of the book. So here's how we used to do it. Some of my students did this as an MQP many years ago. We're trying to determine how much of the material that surrounds the bolt is actually squashed by the clamping. And it's just common sense that the stuff right adjacent to the bolt is going to see the worst load, right? And as I move away, the further I move away, the less load there's going to be in the material. At some point, it's going to go to 0. I can't have that load go forever, right? And I'd like to know what that affected zone, let's call it, is, because if I'm trying to make a pressure vessel, let's make it round, and I want a series of bolts, or if you prefer, the head on an engine, where I have explosions going on in the cylinders, right? And I don't want that to blow the head off. I got to have a bunch of bolts to hold that whole thing down, and if I don't have enough bolts, or they're too far apart, then I'm going to get leaks, because the thing is going to separate under the load locally and let the gas out, right? So we need to know how this load distributes in order to get the proper spacing of the bolts for a given pressure situation, which is common. So a couple of my students did an FEA back, very early days of FEA. This was the first FEA package we had on campus, so this is like 20 years ago. And this little line you see here that looks a little bit like a beer barrel, it's a pair of frustrated cones, cone frusta here. This was the technique that all the other techs promote. I think they pretty much still do, unless they've picked up on Cornwell's work. And so they would say, well, let's estimate the amount of material that's in the clamp zone by the following technique. This piece represents the extent of the head's interaction with the material. So the bolt center line is over here, not shown. The bolt is not shown. The bolt's represented in the FEA by just forces clamping this regime. So that's essentially the amount of the head overlap on the material. Or the washer. If you have a washer, it would make it a little bit bigger, right? And then the idea was we would then take a 30-degree angle and project that down into the material. Whoops. And we would consider that that volume of material, which is now a beer barrel, is the stuff that's in compression, and I'll calculate a K sub m of that barrel, which is a pretty straightforward thing. It's AE over L, but the A is changing. So I can get an average value, right? And this shows an exaggerated deflection diagram for this loading condition, grossly exaggerated, because of course this only moves a few thousandths of an inch when you tighten the bolt. But here's the real interesting thing. We see a lot of deflection right at the bolt, which you would expect, and then it falls off very non-linearly, and over here you start to see a crack open up. So far away from the bolt, we're actually separating the two parts. Because it's trying to go into tension, but of course you can't support tension across a crack, so it just opens up. So that's my leak, right? So I need to know that so I know where to put the next bolt. So I need to put a bolt maybe there, so I don't let that leak occur if this is a pressure vessel. Okay? Well, skip down from 20 years ago when my students did this as an MQP to Professor Cornwell out in Oregon someplace. And this paper that he did, and I don't have the year here, I think it's like 2008 or thereabouts. He did over 4,000 FEA studies, varying the thickness of the material in the joint, the material itself, you know, aluminum, steel, 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 aluminum, aluminum, yada, 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 varying the length and diameter of the bolt, and so forth, a whole bunch of variables. And he did oodles of work. I mean, 4,000 different FEAs, that's nothing to sneeze at. And from that, he developed some equations. Well, the first one of those that I show here is he came up with a better estimate of the bolt stiffness. I've switched now from talking about material stiffness for a moment to bolt stiffness. Now, we had that equation pretty straightforward before. It was AE over L, and we know the area of the bolt, right? That should be a very accurate calculation. What his FEA pointed out was that the head deflection, the head curls its toes under load, is significant compared to the bolt's deflection. And that adds to or takes away really stiffness from the bolt, right? So this equation accounts for the head deflection. And it's simple to do. This D is the diameter of the bolt, L is the length of the bolt. And so he's got this corrected KB prime, which is KB times 1 plus D over L to the minus 1 power. So that's just in the denominator then. And I can then put that times the original expression that we had for KB was this. AT times AB, T is tensile area, AB is the shank of the bolt, and LT is the length of the thread, and LS is the length of the shank. So we can correct the KB now with Cornwell's work. Get a better value for KB. That's useful, but that's not the best part of this. So to define the joint's parameters, he does the following. He says, let's make a ratio called the joint aspect ratio, call it J. It's just D over L. So long, skinny bolt would have a small j, big fat bolt, short fat bolt would have a big J. Yeah? And it would never get to 1 because then you'd have a bolt is, you know, no longer than its diameter. That would be kind of ridiculous. But it could go fairly long the other way. Then we could have different materials between the material and the bolt. In other words, I could have a steel bolt squashing aluminum. So we make a ratio R, which is the ratio of their moduli, so the Young's modulus of the material over that of the bolt. And we could have different thickness plates, right? They don't have to be the same thickness. So he calls a thickness ratio T and says that's T of L over T of L plus H, where L is the one of lower Young's modulus and H is the higher Young's modulus. So, of course, they could be the same. You could have the same two materials, which would simplify that. But so we have these parameters now that are dimensionless, which is handy. And he then uses these parameters to characterize the behavior of the stiffness of the stuff in the clamp zone. And it turns out to be fairly complicated, a little hard to understand when you first read his paper. I actually called him up and talked to him about it because there were some things that were puzzling me, and he straightened me out. But he shows these circles. These are data. These are actual data that he got from his FEA studies, where he's varying the plate thickness ratio as his independent variable here, and showing the joint constant here, and the family of curves is different based on the J factor, which you recall is D over L. Okay? And then he fits some curves, he fits polynomials to these data. That's easy enough to do. You can do that in Excel. And he gets an expression, which he calls C sub t, which has some parameters times the T factor. That's my soft material thickness to hard material thickness ratio here. And he gives us a table of values of Q. Those are the terms, the coefficients in this polynomial, for J factors of various values. This table goes on. I truncated it for interest of space. It goes all the way up to 1. So with this information, I can calculate this C sub t value, which is going to show up later on in another equation. Now, because these all turned out to be nonlinear, and he points out, interestingly, that the nonlinearities are not always the same, because as you change plate thickness ratio in J, I may get a a polynomial that deviates a lot from a straight line, or one that deviates less from a straight line. In fact, this crossover is not in the middle for this case. I only show two here for j.5 and j.1. And so he wants to get a linear expression. And he gets that by taking the two extreme values, which are at the 1 and 0 positions. He calls these CH and CL. So these are the values of C, the joint constant. So you can read off the chart the value for the end point for your particular J and for the beginning point. That's my CH and CL. I can use those in this expression, which is going to give me C. And this correction factor here, which is quite a messy expression, is E, the Napierian base E raised to this exponent, which includes the natural logs of J to various powers. The computer, I don't care. If I had to do that in a slide rule, I'd be having a fit. But with a computer, that's a piece of cake, right? And that's going in here to correct for this offset of the polynomial versus the straight line. So in effect, he's giving us a roundabout way to calculate where we are on those polynomials using his tabular data. Quite clever. So if I follow this process, I have enough info going in. I know what the D over L ratio is for my design. I know what I've made them of, so I know the thickness of the soft and the hard material, or the stiff and the less stiff material, I should say. And I get a value of C, which is quite accurate. And the best part of this is, if I had this, I don't know if I put this in here. Oh, yeah. Here, look at this. These equations, these empirical equations he's developed, match the data from the FEA of all models with an average error of 0.6%. In engineering, we call that on the money. When I got less than a 1% error, I'm done. Stick a fork in me, I'm done. I'm out of here. On to the next problem. This is taken care of if I'm down at that lower level of noise, less than 1%. And he says something else here. He has something about, oh, there it is. And they have a correlation coefficient with the data of 0.9998. You know what that means. That thing fits, his curves fit the data to a fairly well. Okay? This is good stuff. This guy really did a wonderful job. So, and he was very nice about not only letting me use it, but he proofread it after I wrote it to make sure I didn't screw it up. And I had, of course. So he fixed my errors, and so I'm pretty sure this is correct. Okay? Any questions on how to do that? So in my opinion, this whole problem of K sub m has been put to bed with this technique. And you need nothing else but a computer to do this, and you've got the answer. Okay? All right. How do we get the preload in the bolt in the first place? Well, there's a couple of methods here, and I'll show you a few. The tried and maybe not so true method, the classical method, is you go buy yourself a torque wrench. And a torque wrench is nothing but a wrench. It's just a wrench handle. You put sockets on it, and it's got a little gauge of some sort on it. Sometimes they have a nice fancy dial with a needle. Sometimes it's just a stick that points at a number as you bend, and you bend the handle. So the handle deflects. The wrench is made with a handle that is sufficiently unstiff that it actually will bend when you put certain loads on it. So you're measuring the torque from the deflection of the bar that you're pulling on, and it's a fixed length. So we have this fancy formula here to get the T sub I is the torque required to get the initial load F sub I that we've calculated from we get our joint constant C by various methods, and then we find out how much F sub I, what percent of preload do I want? Do I want 50, 60, 70, 80? Okay? And since the bolt has a certain proof strength, I now have a number for force. I'm going to put that force into the thing as a preload. Now I want to know how much torque do I put into my wrench to get that force. Messy formula. It's got coefficients of friction. It's got the thread data. That's the lead angle of the thread. And alpha is the angle of the slope of the threads. 30 degrees for standard UNC thread or UNF for thread. Also for metric, there are also 60 included, 30 on a side. This accounts for the washer friction, if you will. D sub c over 2 is the diameter of the head, in essence, and the assumed coefficient of friction under the head. This is the nut. The noisiest piece in here is the U, coefficient of friction. Because think about this: if the frictions in the threads are fighting me, right? If I have a rusty bolt, I'm trying to get the bolt out. What happens when you put the wrench on it? Most of the time. Doesn't come out, but something else happens too. You shear it. The head comes off, right? Or the nut comes off. Because the friction in the threads is greater than the bolt can stand in terms of torque. And you just keep torquing it with your wrench until suddenly it gives way and you do a torsional shear right across the bolt, and you still got the rusted thing in the hole, right? Well, now imagine I try to put a rusty bolt in a hole, which would be a stupid thing to do, right? And so I got my torque wrench on here, and I want 100 foot-pounds of torque, and I get 100 foot-pounds, but the bolt hasn't moved yet because it's all getting reacted by the rust, the friction in the joint. So it's considered good practice when you torque a bolt to put some oil in the hole first. So I reduce that friction so I'm not stealing so much back to ground, right? I want it to all represent what's in the screw, not in the threads. Yeah? So we can play around with this equation, and we come down and we can put it in a factor, which engineers like to do, K sub I, which is called the torque coefficient. The same stuff is in it as up above. We have tan lambda, which is the lead angle of the thread. Alpha is the tent angle of the thread, if you will, 0.5, coefficient of frictions, etc. And we can calculate this for various combinations of threads. So here is calculated for UNS standard threads with coefficients of friction of something, 0.15, fairly typical steel-on-steel coefficient. And look at the numbers. This goes from a bolt size of 0, which is hardly big enough to see, up to 1.5 inches, which is certainly big enough to see. That's a pretty big range of diameters, right? This is about 1/16 of an inch in diameter, if I remember correctly. It doesn't even exist in a coarse thread. And look at the numbers: 0.22, 0.22, 0.22, 0.21, 0.22, 2.1, 2.1, 2.1, 2.1, 2.1, 2.1, 2.2, 2.2, 2.1, 2.1, 2.1. So regardless of the size of the bolt, my K sub I is coming out 0.22, or if you prefer, 0.21. So this makes it very easy. I take the desired F sub I, multiply by 0.22, or 0.21, and I have my torque, right? Just like that. So pretty easy. But the bad news is that vagaries such as dirt in the threads, rust, all that jazz, is going to make this kind of an unreliable method. In fact, the books will tell you that you can expect about 30% error. In other words, your F sub I might be off by as much as 30% if you dial in the required torque that the formula tells you should use. So keep that in mind. There are better ways of doing it. Now, large structural steel buildings nowadays, they used to be riveted in the bad old days, but now they bolt them together pretty much, and with some welding done too, but mainly bolted. These are very strong fasteners. They're hardened. They're specially designed for the purpose. So they've come up with all these clever self-limiting bolts. I show one example here. This is one bolt in 4 different modes here. Here's what it looks like before you put it in the hole. The shank is quite long, so I don't have a lot of thread left in the clamp when I'm all done. A little bit of thread there. He has a special wrench. Here's the picture of the special wrench. The outer part of the wrench goes on the nut to tighten the nut. The inner part of the wrench, which is reacting against the outer part, goes on this splined spud, which is on the end of the screw. So in essence, the spline stud is holding the bolt, right? It's as if you had a wrench on the head, but you don't. You've got the head by the tail, okay? So I'm holding the bolt by the bottom, by this spline thing, and I'm tightening the nut. And it's designed and calculated so that that spline piece will break off at the right load in tension. So when the desired F sub I is developed in the bolt, pop, off comes the wrench, and you're done. No thinking required. Okay? There's other tricks that they've come up with. This is a load indicating washer. It has little bumps on it that will squash when you get to the right load. So you simply tighten the nut until you squash the lumps, and you stop, and you should be at the right load. These are better because they're directly measuring load, not torque. They're not doing an analog of load as torque. They're doing load as load. So this guy breaks when the axial load gets too high. This guy crushes when the compressive load gets too high. So after tightening, it looks like that. There are other examples as well of custom fasteners of that sort that you can find. I mentioned this the other day, that you will see this statement often in books of this sort. A properly preloaded bolt will never break if it doesn't break during the preloading process. If statically loaded. Notice the caveat of static loading, not dynamic. Dynamic makes a whole new ball game, but because now we got the fatigue factor. So if you don't break the bolt when preloading it, it will never break in service. Why is that true? Well, we have been told that we go close to the yield point. So we look at the Morse circles during and after tightening. During tightening, I've got torque on the bolt. I'm holding the nut, or wrench on the nut, holding the head, torquing the bolt. So I've got twist in the bolt, shear stress due to that, and I'm developing axial stress at the same time. So when I stop turning the wrench, I'm left with the top Morse circle, right? I have a sigma x, which I show on the normal axis, and I have a shear couple, tau xy and yx, making me have a Morse circle like this. Now, as I mentioned the other day, it's considered good practice to unload the bolt, or the nut, just a little after you've gotten to the magic torque, let's say. So you just give it a tap to loosen. You don't really move it very much. You just tap it. And in so doing, you take away the shear stress. You unload the torsion. But you don't move it far enough around the threads to really take away the axial load, right? And your Morse circle suddenly goes from that to that. So if it survived the larger one during the loading, and I only put tensile loads on it statically from now on, it's never going to break. Okay? That's the reasoning behind that. 2 more slides or 3 more slides and we're done. Fasteners and shear, I already talked about how the buildings are put together with fasteners, and those are loaded in shear. This shows such a joint, 4 bolts holding it together, but what I really want to have happen here is I want to preload these bolts so much so that the normal force between the 2 plates is so high that the friction force in there is supporting the load. And the bolts don't see any shear. Okay? That's the name of the game. I want the friction to take the load, not the actual fasteners. This is done in the construction industry, as I said. The problem with asking the bolts themselves to take the load in shear is depicted here with some exaggeration. First of all, the tolerances on the diameters of bolts are not very tight. They're quite sloppy. And tolerances on multiple holes have issues as well. I'm not going to have them exactly the same distance apart on the 2 pieces. And that's somewhat exaggerated here, where you see the top plate hole on the right is shifted to the right quite a bit. So this leads you, as a matter of practice in machine design and any kind of engineering design that involves fasteners, you always make the holes for the fasteners bigger than the diameter of the fastener to accommodate for the tolerance of the center-to-center distances being off. Okay? So you can get them in the hole without a hammer. As a result, then, I can't really rely on the bolts helping me in shear because they're not even touching the size of the hole. Right? I have to rely on the clamp friction. In machinery of the type that we've been talking about in this course, which is typically medium to high precision machines, we're not talking, welded together junk. We're talking machines that make products at high speed and high quantity and last a long, long time. They have to be very well designed and very accurately made. In those instances, the rule is you never put a threaded fastener in shear, period. Not allowed. You use threaded fasteners to develop tension only, from which you can get an awful lot of friction force so that things don't move in shear. That's one thing. But also, to guarantee that it stays where I want it in shear, I add something called dowel pins. Now, dowel pins are off the shelf. They're made to an ANSI standard. They're half-hard to full-hard steel. They're ground to a beautiful mirror finish. They have a tolerance of the order of 1/10 of a thousandth on the diameter, plus or minus. That's a very tight tolerance. And they're relatively cheap. You buy them by the box. You know, 144 at a whack or whatever. And they're made by high-speed automated machines, so they're not expensive to make. And they are used for positioning and for accepting shear loads if, in fact, the friction lets go, which we hope it doesn't, right? So just a brief description of how you go about putting together two parts in a machine that has some precision to it. I'm going to use the bolts to hold things together and nothing else. So there's good clearance holes around the bolts. I'm going to pre-drill one of those two parts, the top part, with holes for the dowel pins that are actually a little smaller than the dowel pin. So my pilot hole is a little bit undersized, okay? I put the assembly together. I do whatever alignment and other fiddling I need to do to get the thing to work correctly, right? And then I take out my drill and I go into the pilot holes in the top piece with the same diameter drill, then I drill through the second piece. So now I have two sets of holes that are exactly in line, no tolerances involved, because one made the other, yeah? Now I take it apart. I take it to the shop. I get the proper size drill for the bottom, which is going to be a press fit, and I get the reamer out. I enlarge the hole a little bit, take up my reamer, I ream it until I get the right dimension, and I take a mallet and I drive the dowel pins in. Bing, bing. So now I got dowel pins caught in the bottom piece. Now I take the top piece, I get another reamer, and I ream those to have like 1,000th clearance. A little bigger. I put it back together, it drops right together exactly in the right place. When it gets taken apart for service later on, it gets put back together in exactly the right place forever. If I want to get the dowel pins out, I take them to the arbor press, punch them out, and do something else. Okay, so it's not irreversible. So those dowel pins now provide me with accuracy. They're hardened steel, so they're strong as the dickens. They give me some good shear resistance. I can make them as fat as I want. And a typical arrangement is, as you see here, 2 dowels to give me a moment, right? And some number of bolts to squash everything together, typically 3 or 4, depending on the situation. And I now have a reliable, accurate, repeatable assembly that will last a long time. Okay? That's it for fasteners.